All right, welcome back. My name is Jesse. I am a tutor and a business owner in Melbourne, and I also sat the GAMSAT in March of 2021 and scored one of the highest scores, scoring 100 in Section 3. And so what I've done is created this channel to basically make videos and free resources for other candidates that are sitting the GAMSAT, because there's not enough high quality, or hopefully this is high quality resources that are also available for free at the same time. Hopefully these things you can get a lot of value out of. You can improve your score as well. I try to make them as kind of actionable and skills based as possible. There are some content related stuff. Today's one is going to be looking mostly at skills, looking at the skills of graph analysis. I guess this comes more so from the maths domain of the test, but you'll see it being used across biology questions, chemistry questions, and the physics questions as well. Running through some of the things that I used for reading graphs really quickly and kind of cutting out a lot of the noise of the information or of the stem. And then we'll also go through all the different types of graphs that we commonly come across in it, and some of the specific features and ways to kind of break them down and things to look for based on what I've seen ASA actually assessing in the tests. Even though this is not going to be a substitute for actual physics, chemistry, or biology knowledge, it is a reasoning-based test, and particularly for the bio questions, a lot of it is just about being able to recognize patterns, understand relationships, and make conclusions and extrapolations from them as well. All right, so I've put already, I wanted to pre-prepare the notes. Sometimes I scribble them on screen. Sometimes I'm a little bit messier than usual. My handwriting's never great to begin with. I figured I'd do it a little bit more neatly beforehand, and then we'll scribble on here. Cool, so the first thing is we've got just some general tips. First thing is just scanning the axes, right? So always check whenever I get given a graph, the first thing I do is go straight to the two axes and I try to understand what variables am I being given, and then what are the units that are being used, and then moving from there how to read the graph. I don't actually try to draw any information from the graph when I'm reading. I wait until the question at that point. So all I'd be doing here is scanning through and getting a sense of what kind of scale I'm dealing with. Some of the common ones, I'll leave off obviously linear scales, which are just standard numbers. We're going to start with if they give you a log scale. So if they give you a log scale, say here I've done an example, log of bacterial population, 1, 2, 3, 4, 5, 6, and then we've got pH, which is technically not a log scale, but let's just leave it at that. Then immediately we need to understand what a log actually means. So most of the time in GAMSAT you're dealing with standard logs. Anything else like natural logs or logs with different bases, they will give you the approximated decimal for it if they're going to use the actual maths side of it itself. Otherwise, you'll be using standard logs. Standard logs are expected that you'll know how to read and understand them. So effectively, a standard log is anything with a log with a base 10 of something, right? X, we'll call it. It could be any variable. The quick way to read them is when you're logging a number, a standard log of a number, however many zeros there are, if there's a 1 in front, however many zeros there are, that is the log value. So there are 4 zeros. So the log 10 of 10,000 is 4, right? If we were to be logging something that was not starting with a 1, say 20,000, then what I would do is go, well, the log of 10,000 is 4, 20,000 is above that, so it's going to be a little bit more than 4, but it won't be anywhere near 5 because 5 would represent a log of 100,000, 5 zeros. So then I can estimate that and call that maybe 4.2 or something. Coincidence with the 20,000. Estimation would be fine for anything beyond that. And so really what you're dealing with is when you're dealing with log scales, is you're just looking at an order of magnitude. So because we know that standard logs, log 10 we'll put, then it means this number just represents the order of magnitude or the number of zeros. So 1 would really represent a 1 with 1 zero, 2 would represent a 1 with 2 zeros, and so on. So you can see 1 represents the tens, 2 represents the hundreds, 3 the thousands, and you could just keep going from there on. That's the first one. And then the next one is scale alterations. So this is where they put in extra things like in the units, they'll say in the thousands, for example. So if this says 3, that really means 3,000. It's representing it in groups of 1,000. Or they might do something like this in exponential or scientific notation, where they put times 10 to the power 6, so that is millions, effectively. So I've put here the common prefixes, N for nano, 10 to the negative 9 standard units, then mu for micro, 10 to the negative 6, a millionth, and then little m, so for milli, 10 to the negative 3, a thousandth, C, centi, 10 to the negative 2, hundredth, deci for a tenth, K, only lowercase value for large numbers, but K for kilo 1,000 times, M for mega 10 to the 6 a million times, and G for giga 10 to the 9 billion times, right? So look out for those because you may have to adjust the number. The number on the scale won't represent the actual value that you need to use, and that may be the trick in the question. And then finally is broken scales. So if you see either a double dash line or a little zigzag like that, all that means is the scale is not continuous, so you can't assume that at the axes that x or y is equal to 0. You have to start the count. So we might see, for example, if I get rid of those, we might see something like this that says 5, and then you'll see it just do 6, 7, 8. It means that there is no data that exists below 5, so they didn't want to waste space having 0 to 5 shown, so they've just kind of cut it there. What that means is if you had a graph that was doing this, you cannot assume that this here is actually the true y-intercept, right? Because this does not represent x equaling 0, because the scale is broken, unless it were to state it that way. So this would not be the x-intercept, or the y-intercept. And then slopes and gradients. This is the next feature I look for. So once I've scanned the axes, then I might look at, all right, what's the slope doing? A lot of questions are relating to slopes and gradients. And these are effectively just rates. So remember that the slope represents the rate of change of something, and it's always the rate of change of y against x, or y per x. Per x, or we could say the vertical axis if you prefer it that way, per whatever the horizontal axis is, right? So linear graphs or straight lines implies that the gradient or the slope is constant, and so therefore we can use some of our mathematical rules, rise over run, or using it from actual coordinate points as well and actually map it out. More importantly though, they often don't get you to actually do calculations. You might do rough estimation of them, but more than likely you'll just be ranking different graphs based on their steepness. So if something is steep, it has a high rate, flat, low rate. And when I say steep, it doesn't necessarily mean steep positive, it can mean steep negative as well. So this would be a maximum or a very high rate of increase. And this would be a very high rate, but of decrease in something, right? So look out for that. Flatter is where they're going to sit almost horizontal, right? So this would be a lower gradient or a lower slope overall. Cool, and I'll just change this here. That's high as well. So a high decrease, this is a high increase, like that, whereas this is a low increase, and then this is a low decrease or a slow decrease. Then exponential growth and decay is not linear. So we've got two different types. So growth, common example would be cell population size. And so we'll see this curve upwards like a plane taking off, although more like a jet. I guess planes wouldn't want to go vertical. And if we map it out, we can see that for every standard jump to the right each time, doesn't matter what that actual interval is, as long as it's consistent, we can see that the rise each time is getting bigger. So here it was this big. If I then drag this across, you can clearly see it's about 2.5 times bigger. So it means that it's steepening up as it goes. It means the gradient is changing and increasing, which means the rate is also non-linear, and it's not consistent or constant. The rate is growing, so that would mean it's going faster and faster. So again, if that's cell population size, and then this is time, that would mean that the population is growing at a faster and faster rate every period of time. We can also do that from tangents, so you can draw straight lines that just touch the graph once, and you can keep drawing tangent lines at different points, and you can see that they're steepening up as you go. Then exponential decay looks like the complete opposite. That one slopes down like a slide, and the same thing if we take even incremental jumps to the right, we can see that the jump down gets less and less each time. So this would be something like radioactive decay, for example. If it had 100% of the sample there, let's call this 1 half-life. We'll just do 1/2 L. Then it would drop by 50%, right? Down to 50%. But in the next half-life that it goes across, it's going to drop by half of what is there. So that is 25% of the original. And then there 12.5%. And so on, it'll approach 0 over time. And then S-curves. So these come up more in chemistry questions and biochemistry kind of related questions. So we see them in pH titrations or acid-base titrations, and you get the equivalence point in the middle where the gradient is at its steepest point. So that's why I'm mentioning it, because it relates to gradient still. And you can see the gradient starts off very, very low. It then becomes very positive, and then it becomes less positive, but still positive. So if you got a question relating to rates or rate of change or speed or anything like that, what I would do is, my notation was I would either use numbers. So I'd go, well, here the gradient is 0. Then I might say, oh, it's 1, then it's 2, then it's 3, then it's 4, then it's 10. And then it starts to soften off again, 8, 7, 5, 4. Well, it's a little bit wonky. Let me try that again. 10, it might be symmetrical. Then 4, 3, 2, 1, 0. Like that, to understand what it's doing, and I can see that it's still always positive. I might use tangent lines. I can see they're, no matter what, always pointing upwards to the right, so they're always positive. And then the other option I might use is notation just with little pluses. So I'd go 0, and then I'd put a little plus because it's just positive, then a slightly bigger plus, then an even bigger plus, and then a really big plus, and then a less big plus, and then smaller again. Like that, and back to 0, like that, to help understand the relative size of the slope. And then the other thing to think about is the curvature as well. So what's the rate of change of the rate of change? For anyone who's done calculus, you will not have to use calculus in this at all. That's well beyond the maths kind of topics or expectations in GAMSAT. But it is good to understand what curvature means from a qualitative perspective. So here, the curvature is positive through this region because the gradient is increasing over time. Whereas here, the gradient is decreasing through this section. So here, the curvature is actually negative, meaning that it's still increasing, but at a lower and lower rate, or it's increasing less and less each time. A simple way to think about it, though, to understand any kind of curvature, is just to go, what is the gradient doing here? What is the gradient doing here? And what's it doing in between? It is increasing. So that is a positive curvature. What is the gradient doing from here to here? Technically, this would be infinite, right? But we're not going to go there. Here it's back to 0. So from here to here, it is decreasing. So that is a negative curvature, like that. Cool. Same thing. So hemoglobin dissociation curves, you can also get these operate in the same way. But with these ones, you'll often look a little bit more at concepts of shifting the curve. So we might have 2 species or 2 different conditions being shown, and the hemoglobin saturation against the partial pressure of oxygen in the blood, or partial pressure of oxygen in the air, or wherever it's being measured. And so we often look at this point in the center, which is usually the 50% saturation level, as a comparison. And we look at it shifting, and we look at what the change in the pressure is. So you can see that both the gradient and the axes become the key tools that you use to break down graphs overall. And so in this case, a shift to the right, I've put here, what would this actually mean? What does a shift to the right actually mean? To saturate 50% of the hemoglobin in the red blood cells, you need a higher partial pressure of oxygen, which means that is not a good outcome. It means you're requiring much higher pressure of oxygen in order to saturate the exact same level, which means that the ability to take on or saturate the hemoglobin is lower in this case than standard. If it's shifted left, that's a good thing. That means that you can saturate with less oxygen pressure, which means it's easier to saturate overall. Cool. We often don't really talk much about the kind of plateau ends there and there. Then area under the curve. So these are a little bit more physics-based. So a simple way to think of what the area under the curve represents, rather than just memorizing every single graph and what the area might represent, is think of, well, area of a box or a rectangle is length times width. So the area of a graph, regardless of the shape, even though you may have to do calculations, area is some version of length times width. So if we think of the x and the y-axis as our length and width dimensions, whatever they are will give you, it'll calculate the variable that the area represents. So if, for example, this was a speed time graph for physics about something moving, then I would go, okay, speed times time is length times width. That's the area. And what's speed times time? It's distance. So now I know that the area under the graph is going to be total distance. and that might help me answer a question like that. If I wanted to then get average speed, I know that average speed is total distance divided by time. So I could take the area divided by the interval, and then I've got my average speed instead, like that. So I'll get rid of that so it's not confusing. And you can do that with literally any variable. You'll find some of them have variables or units that don't really make any sense. And in that case, you won't be asked about the area of that particular graph. It really only comes up in physics more than anything. That's it for all of the skills, right? Then we've got graph types. So the first one you should already be pretty familiar with is standard line graphs. So this is just looking at analyzing two variables, usually an x variable and a y variable of some sort on the two axes. So for example, say here we've got wing flap frequency of some kind of bird or insect and air temperature. I'm using this because I'm sure you've probably seen something similar in ASA material. They seem to love air temperature and birds flapping their wings and their velocities and things. There seems to be a real trend there. And let's say all of these different lines here are separate graphs. You wouldn't normally be given all of these onto one, just overlay them to save time and look at the different features of them. You can see that let's start with the red one. It's linear. So what that means is that there's a linear and a positive relationship, meaning as air temperature increases, the wing flap frequency increases at a constant rate. We can make that assumption. And a lot of graph reading is about being able to make assumptions to answer qualitative questions, rather than technically reading the graph or calculating gradients and things like that. It's just understanding what something like the gradient or the variables actually tell you. Let's do the blue one. So the blue one, the light blue one, says that the wing flap frequency for this particular species is very high, and then as temperature goes down, it actually drops off. It decays exponentially as well. And so this is exponential decay. And so therefore we can assume that as air temperature increases, the change or the drop in wing flap frequency is less and less each time, because we understand that the mechanics of how exponential decay works. So it's often recognition of the shape itself and understanding the mathematical relationships from a qualitative perspective. Then the green one has a plateau in it. So what this would suggest is that it prefers lower temperatures. Sorry, it doesn't prefer lower temperatures, does not like lower temperatures, does prefer higher temperatures for higher frequency. But it gets to a point where about here, it effectively flattens out. And what that means is that there's no longer any benefit or any increase in wing flap frequency beyond a particular temperature. That would be a plateau in that case, unaffected. Then we have plateau. I don't know, I'll leave it to people who know French or something like that to spell that one. I think it's that way. And then the dark blue, so this one is our S-curve. So this would suggest that you get the most benefit or the most increase in wing flap frequency in this kind of middle region of air temp. It's not very responsive at low temperatures, and it's not very responsive at high temperatures. You can see we're starting to get qualitative analysis out of it. So that's our S-curve. And then the pink one means that it's completely unaffected by air temperature, right? There's no gradient. The gradient is 0. So that means that the wing flap frequency remained constant regardless of the fluctuation in air temp. So that is, we'll just say 0 gradient, which we can make the assumption then that temp is unrelated to frequency for that particular species or that particular graph. And then a slightly different one, I thought I'd do this on a separate axis, is a kind of distribution curve. So here we have enzyme activity over pH range. And so what we're more interested in here are the turning point, right? So turning points represent maximums and minimums. That is our key feature. Anything where it's 0 means the activity is nothing and it's not working very well. But we just want to understand what the position of that is, and that will then tell you something about the optimum pH for that particular enzyme. And so these are the 3 things that I'd be looking for when I get a 2-variable graph: is slope, are there turning points, and are there any points where it plateaus or flattens out as well, and understanding what that means in the context of the question. The next one is comparative line graphs. These ones do catch a lot of people out. I know I got tricked by a lot of the axes and things in my practice on these. So I've tried to mock up a simple example of this. This is where you have 3 or more variables to deal with. So although you're limited to just the X and the Y axis, they can then create these fanning lines that bring in a 3rd variable. In this case, I've gone with oxygen saturation of blood against temperature and velocity. And so pretty much what you want to do here is wait for the question to guide you on what you're actually looking for. And it may say something about like, for 20% oxygen saturation, right? So it's holding that variable constant. What that means is stick on the 20% line and don't look at anything else. Then it might say at a temperature of 10 degrees or something, and it might be here, and you go up, and then it asks you for the velocity, and you can read out like that, or vice versa, right? So the idea is that you hold one of the three variables constant, and then you test the relationship between the remaining two. The graph is there to just disguise it and confuse you into thinking you have to be paying attention to more variables. If they're just getting you to locate a point, then they may just give you information about all three, and you literally just kind of map it and point to it. Those are probably the easier ones, and you won't see many of those. If instead they're saying for a particular temperature, that is where we would use a vertical line and hold the temperature constant at whatever temperature it is. And then what we can do is we can test the impact of one variable on the other. So if I want to increase velocity and see what that does to oxygen saturation, then I effectively just bounce from low. I always go from low to high. I always try to increase one variable and then see what happens to the other. So low to high velocity, what does that do to oxygen saturation at this particular fixed temperature? It starts down here. So it starts at 100%. And then it seems to jump as I jump up the line, because I'm following the orange arrow, I'm bouncing onto new oxygen saturations. And I can see that's a decrease. So now I know there's a negative relationship between velocity and oxygen saturation, like that. I could do the same thing if I wanted to hold velocity constant. So say this was a bird flying at 20 meters per second or something. That's crazy fast, but we'll go with it. 20, maybe that's here. I would now hold this constant instead. And let me just highlight that. Hold this constant. And I might want to see what the temperature does to the oxygen saturation. So in that case, I'm going to increase the temperature at this fixed velocity. And now what's going to happen is I'm going to start at 20%. And then I can see that as I run along the red line, it's jumping to higher and higher oxygen saturations. So that means there's a positive relationship between temperature and oxygen saturation in that case. You can also reverse it. So you can look at like, what's the impact of oxygen saturation on velocity as well, although there may be a bit of like cause and effect relationship that's being reversed there. But so at a particular temperature, I might hold the temperature constant here. And then if that would be decreasing it that way. So I might go this way. So I want to, again, increase the oxygen saturation and see what happens to velocity. So I have to basically bounce from here to here, here to here, and here to here. So as I increase oxygen saturation, velocity, I'm on this axis here, goes down. So there's a negative relationship between them, which we proved before anyway. There was a negative relationship, velocity to oxygen sat. So reversing it would have the exact same effect as well. Cool. And so this is what I refer to when I talk about vertical line testing, horizontal line testing, and so on. Another way to do it is you can actually take the line itself and you can kind of drag across like this, and you can see what happens to each of the variables. Then we also have some other ones like this. So in this case, all linear, 3 different species. And we're looking at water salinity in ppm, so this might be fish, in parts per million, and then velocity in meters per second, maybe swimming velocity. So you can use concepts from something called linear programming if you were trying to work out the ranges over which you had the fastest species. The quickest way to do it is just kind of scan along the top end here. So we can go like this, and I'll switch colors each time. As soon as you switch lines, switch colors. I mean, obviously you wouldn't have that luxury in the real thing, but there we go. And then you can just map who's better at what. So basically the fastest swimmer from here to here, say this was 8 degrees and this was 12 degrees. From 0 through 8, the fastest swimming species is species C. From 8 through 12, the fastest species is, I follow the yellow line, species B. And then species A is better in higher temperatures. so on. They might have a question about like tropical water or this or that, and you go, oh, well, probably the green species A swims fastest, like that. And this is how we can kind of very, very quickly break down the graph into sections. You could do the same thing for lower. You can see on the lower end, one of the species does not get involved. So you could use this as a reasoning as to which species is on average the fastest swimmer. And so that would be the one that does not get involved. So up here, that would be species B. Seems to never really be at minimum velocity. So that would probably be the all-rounder overall. And then finally as well, you can look at points of intersection. So this is where not only are the variables equal, but it also means that there's a point of indifference. Yeah. So if there was a choice between two species, we would be indifferent in our choice. It's a good way to think of it. Not really sure what the context of that would be, but keep in mind, point of intersection is also a point of indifference. And then vertical separation. So vertical separation, you're looking at the deviance or the difference between them. So if, for example, they said at what temperature are species A and B most different from one another in terms of their velocities, I'd effectively be going, all right, well, species A, which is this line here, and species B, I think I said, or species C. Let's go with species C, I can't remember. Where are they most different? So I'd be looking at this vertical separation, because that is the difference. Clearly through this middle section, they're very, very close together. Further away, they've got larger, larger differences. So visually, it looks like either at 0 degrees down here, or all the way up here looks about equivalent. Let's just call that 30 degrees. At extreme temperatures, they seem to differ most. They seem to be more similar in kind of middle run temperatures of maybe 15 degrees. Then we have distribution curves. So distribution curves, I mentioned those before with enzyme activity. So you can also have them in physics questions relating to wavelength of light and the absorbance of that light, and a couple of different examples. The only things you really want to look for here are the position of the maximum point and the spread of the data as well, the spread of the graph. So you can, if you want to compare the absolute values or positions, just go for the maximums. This would be x1, this would be x2. So clearly the blue graph has a higher wavelength of absorbance. Spread analysis is about how wide the graph is. So in terms of which one is more adaptable to absorbing different types of light, that would be the blue graph. So it seems to be the winner all around, if that was to be a good trait. It's much, much wider through kind of the majority of it or so. And the same thing if I do it with the red, it's clearly not spanning as big of a range of wavelengths, so it's a little bit more specific. Those are the only things you need in any kind of distribution bell curve. And then grouped bar charts. So we're all familiar with bar charts, I think, but grouped bar charts, there's some tricks to reading these really, really quickly. So the first thing is you can isolate a group. So if the question is just in relation to one group, focus just on that group and ignore everything else. It's often just about pulling out the right information without getting overwhelmed by the amount that's in front of you. So say this was some kind of experiment about plants and you've got those in light, those in dark, those in a bit of both. And then we've got two variables. Negative will mean that the variable is absent, and then positive would mean the variable has been added. So effectively two independent variables with one control group being this here, and then you've got a bunch of experimental groups repeated. And then we're seeing the impacts on survival rate in percentage. We don't need to know any more context to that. So if we got a question about those in light and comparing the impacts of the variables, stick here and then look at what's happening. So from the control, we can see that adding variable 2 caused an increase, adding variable 1 caused an increase, which technically I guess should go from here to here. So both variables caused an increase individually. However, it caused a decrease when you add both as well. So there's some kind of connection there, and you could answer a question just on that. So that is group isolation. Then probably should have done that in red. Let me color code this. That should be in red. Let's do it in blue now. So connecting the tops. So I've kind of done that there. If I wanted to understand the relationship between them, then you can see I just did this, and it helps me just understand increase, decrease, that kind of thing. And then error bars, I haven't got those shown on here, but as long as we know how to read them An error bar might look like that. It's a relative accepted deviance around our data based on some error margins within our calculations. So it means that although we've measured it to this point, it may actually in fact sit up to this high or a little bit lower as well. And there'll be some confidence interval associated with that, as long as you understand that taller error bars means less trustworthy data, and shorter error bars means much more reliable and trustworthy data, like that. And then isolating specific bars. So you might instead want to do an analysis of this variable, the light presence, right? And so what you would have to do is, to hold everything else constant, is isolate one of them. So for example, you could take the control and then it's effectively staying flat. And then from here to here, oh, actually that's not it. Decreasing. And then we can understand a relationship there for the control in that case. It means that light or dark makes no impact. Mixing the two seems to not be good for survival rate for whatever reason. Wouldn't make any sense for a plant, but I've just made this data up. If we do another one, and again, I've not stuck to my color coding, let's go to purple. We might do, for example, the second bar here where the second variable has been added. So what happens as we add or take light away, it seems to not have any impact again. And then there's a slight decrease. So we've got a consistent relationship. Then I might go for this one. So what about when we add just the third variable? That one seems to be completely different, right? So that one seems to be impacted. And then there's the same old decrease. So we can start to understand then that any changes in this group are probably due to the first variable, because the third bar, which had the first variable added without the second one, explained it, and the second bar explained that the second variable had no significant impact relative to the control. And that allows you then to isolate individual elements and then understand the relationship as well. So isolating specific bars. Then we have stacked bar graphs. So again, just being mindful that to read them, you're actually just looking for the widths of each section. So if the green one, for example, relatively easy, just connect the tops and bottoms like that, and you can clearly see that it's getting bigger. So there's an increase overall. If we look then at the purple though, and we connect tops and bottoms, look at the width of it. Don't look at the actual direction that the graph is going in. And you can see here, the first two are effectively running parallel to each other, which means there's no change. And then here they're cinching in. So that means that there's a decrease, and then cinching in again, decrease. So no change here, but then decrease and decrease through there. So a general decrease, whereas a general increase here. And then this one, we can just go right across the top there. And we've already done a lot of the work. We can see that seems to be a bit discontinuous, or it seems to be a bit inconsistent. It decreased, then increased, and so on. You can get qualitative analysis just like that really, really quickly. Sinusoidal graphs, again, more of a physics thing. You'll see them in AC voltage, sound waves, any kind of transverse waves as well. Harmonics, glottal pulse, we saw that in some of the practice material, and respiratory volumes as well from some physiology. All we need to, again, understand is just some of the key features. We're looking for amplitude, which is the deviation from the center to the maximum, or the deviation from the center to the minimum, but not the whole way across. The whole way across is 2 times the amplitude, so be very careful about that, unless it specifically defines the amplitude as being max to min. That's not a standard thing though. And then the period of the graph is the width of it before it starts repeating its sections. So if I was to continue this graph, you would see a complete carbon copy of that section, and then it would just do this. It would just keep repeating, and so we can chop it up into repeating cycles, and the width of that is 1 period. And if this is measuring time, then frequency is 1 divided by the time interval of one of those periods. So if this was 10 seconds, for example, then frequency would be 1 on 10, and that is measured in hertz, like that. And those are the 2 things you can usually answer the questions just based on qualitative analysis of those 2 features of the graph. And then finally, so then we've got these pseudo-ternary phase diagrams used a lot in chemistry and maybe in some biochem type stuff as well, looking at effectively the composition of a compound. into 3 different groups. You can have more complex ones with pentagons and that kind of thing. I've not seen those being used in GAMSAT. They could, but the principles are the same. So what you want to do first is make sure that you use a known point that they give you to understand how to read the graph. If they don't give you that, you can usually work it out by picking a random point. Try not to pick one in the center. Try to pick one where the numbers won't all be the same. So I've picked one here. And effectively, you can just branch out in 3 directions, and you have to go to all 3 walls of the triangle until the proportions add up. And they should also not run in the same direction as each other. So that one can't work. You can see I've already run myself into a problem. I can't go this way. I can go that way, but then that hits that wall, so that's not going to work. And you effectively just learn how to get it to, there we go, hit all 3 walls, and then you check 0.2, 0.4, and 0.4. That all adds up to 100% effectively. So that means that this is the way that I'm going to read it. I'm going to leave that on there, and on the scratch paper, I would just scribble down a triangle with just the line. So just like this, without all the detail, and just go like that. Oh, a little bit wrong. Like that, so I remember how to read it. And so then they might talk about, well, if something is to have, 0.4 of class 1, 0.2 of class 2, and then something of class 3, I don't know if this is going to work, then I would go, okay, well, that would mean, I'll go a different color, go with pink. Class 1, 0.4, then class 2, 0.2. Oh, I've picked that one. There we go. And then the third one left, I have to go in this direction, points me at 0.4. Again, you can do it in a different way. So let's say this is 0.6 and this is 0.2. Then I would go 0.6, 0.2. So I'd line it up and I'd just run a line right across like that. And then 3, this would have to be the leftovers, which would also have to be 0.2. And then I can see there, they actually don't cross, which means that is actually not a possible compound in that case. And this is effectively how you read them. Most of the time, they'll get you just to find the point or read the axes off of a given point to know the proportions of 3 different compounds or 3 different ingredients in a chemical compound. There we go. So that is pretty much everything. That's like my rundown of all the things. I may have missed some graphs, but I've gone through all of the material, how to think about what I've seen in past exams and stuff as well. There may be some things, particularly the bar graphs, you may be able to use that in section 1. They sometimes have some qualitative analysis in section 1 with some graphs. So that might be helpful there as well. But yeah, hopefully this is helpful. General tips: scan the axes, check for the scales, check they're not alternating them or changing them. Think about what is the slope and what is that telling me. Area under the graph as well are the 3 key things. Then in terms of all of the different graphs, they each have unique features, something that you could probably make a cheat sheet on, have that with you and practice, and then start to remove that as well as you get more and more comfortable with them, and maybe adapt that cheat sheet based on mistakes that might happen as well. Cool. All right, I think this one has gone on longer than I wanted it to, so I'm going to cut it there, and then I will see you in the next one.